Welcome back to our study of integral calculus. And in our last video, we introduced the concept of kind of area under this function, area under the function, and we were adding up changes in velocity times time, and we were adding up calculating distance by finding this area under the curve. And in that, we did the following. I started this video here, where we've used these rectangular approximation methods in order to do what? Well, we had a little curve, we had a function here, curve, and we found, we might find the area between A and B, right? And we were adding up that rectangle. We had to figure out a height for that rectangle, that rectangle, that rectangle, this rectangle. Okay, so in this case, I've drawn 1, 2, 3, about 5 rectangles. We call this would be the right-handed rectangular approximation method. And what this was, these rectangles, this was the height of the rectangle. And this delta x would be the width. And we usually, if we had uniformly wide rectangles, we'd say that width is equal to b minus a over n. You'll see this in a book, so I put this down here too. This is something to note, that you'll see things like we use Riemann sums, and it's an example of a Riemann sum. We sum these up. Now, there's always error in our approximation, right? Sometimes using the left endpoints gave a better approximation. Sometimes the right were better. All the time, if you use the trapezoidal method, you get a more accurate representation. But if you wanted to do more work, how can this sum give a perfect answer? If you wanted to really do a lot of work, how would you get a perfect answer? And you'd be correct if you said, well, just add up more rectangles. Make these delta x's skinnier. Make these skinnier and make n larger. So essentially, I'm going to let that thing get kind of infinite. And I'm going to let that thing go to 0. Okay? So I can intuitively do that. If I want to do it in a mathematical way, I'm going to use some limits to define it, okay? So if I want a perfect answer, I'm going to let that limit, I could write down something like this, okay? The limit as n goes to infinity of this summation, right? The summation of k going from 1 to n. So here's my n sums of f. Here's the heights of my rectangles. The height is f of xk. At every one of these k values, I get a new height. And then the width of this might be b minus a over n. This is what I've been calling delta x. Okay, what is that equal to? Well, if I let the limit as it goes to infinity, we've got a new symbol, and we refer to as this integral from a to b of f of x times dx. Okay, so again, when you write this, there's a dx. This is the, let's say, think of this as the infinitely thin width, and this is the height. So we're still adding up areas. There's a reason why we wanted to start by adding up areas, so we could we'd get some intuition before we just gave you this notation. And when we start with that, let's call this is what we're calling the definite integral. The definite integral. When you look at problems with the definite integral, I think one thing you can do to help you understand the problem is to pay attention to units. Okay, so I'm going to say units here. And I'd show you this. If we say we integrate from A to B, v of t, which is what we started this whole thing with. We had a velocity times time. Now notice the units of velocity are going to be meters or feet per second, times, this is a multiplier here, multiplier there. The dt, the width of this thing, is going to be in seconds. So you see what I'm really adding up. This is a big adder. An integral is a big adder. I'm adding up meters. Adding up meters. Adding up meters, and essentially I'm calculating distance as long as velocity is always positive. This would be distance traveled, okay? Again, if you see another problem, just to emphasize this and have a little, let's say I was integrating this, and I had an integral f of t times dt. And the units of my f of t were ladybugs. Ladybugs per minute. Well, if the units of dt was minutes, and clearly I'd be adding up ladybugs, okay? So adding up ladybugs, what does an integral do? It's a big adder. It's going to add up here little units of ladybugs over time to calculate the total change in 8 ladybugs from A to B. Notice another thing, when you look at this symbol here, I'll go back up here. When this says dx, I'm integrating over x. These things have to be x equal. This is not how they write the integral, but remember, this is x equal. So since this is dt, this is time equal A, time equal B. Okay, this is dt, so this must be time equal. Okay, so now we're starting into integral calculus. We're adding things up, and we'll have a lot of properties of things, these things that we need to study. Now that we've introduced the concept of this definite integral being the exact area below the curve, now I need to really tell you about properties of this, properties that we'll use in solving problems, and some gotchas. First thing I want to tell you is, maybe I should put this in, that integration is not equal to finding area. My handwriting seems to get worse. It's not really that bad. It's just on this thing I write on, it looks bad. Integration is not equal to finding area. We've been talking about area under the curve, but a function doesn't always stay positive. Okay? So for instance, let's draw one of these guys, and let's assume we're going to go from A to B to C, and the function here is, now the area under this curve is A1, and we're going to say A1 is equal to 15. The area down here, the area below the axis from B, this right here, this being A2, A2 is equal to 10. Notice it's below the axis though. A1 is above the x-axis. If I want to say the following, from A, if I want to say the integral from A to B of f of x, well, here's area all above the axis, and that is just going to be equal to A1. or equal to 15. So there the integral is exactly the same thing as finding the area under the curve. Now if I wanted to integrate from b to c though, of f of x, the area between the curve and the f-axis is 10, but that's below the x-axis, so this is actually going to be a negative a2, and that's going to be minus 10. Also, if I wanted to integrate, say, from a all the way to c, if I wanted to integrate from a to c, the whole interval, well, you might guess, what's that equal to? That's just going to be a1 minus a2. That's going to be 5. So when we integrate, it's not, we can use integration to find area if we know what we're doing. But the integral and area under the curve are only the same if the function's positive. We have this concept, we might say, of negative area. So integration is not equal to finding area. And it's really the same thing as saying velocity is not equal to speed. They're equal to speed if velocity is positive. And also you might say, well, displacement. Finding displacement or finding the change in position is not equal to finding distance. Okay, distance is always positive. Okay, so keep that in mind. We talk area, but they're not the same thing.